Good afternoon, everyone. This section is 4.9, and it's all about anti-derivatives, or an introduction to anti-derivatives. And as I've mentioned a few times over the course of this class, there's three main things that are talked about or topics in Calculus 1. One of them is limits, then you have derivatives, and then anti-derivatives, right? So this is kind of like the third part of it right here. And it's pretty much you're going the reverse direction of the derivatives, okay? But we're going to talk about some notation before we get into that. So we have a function f, notice I'm using the uppercase f, is called the antiderivative of a function f on an interval I if big F prime of x is equal to f of x for all x in the interval. So what does this weird notation mean? Well, whenever we have the uppercase letter, that denotes the antiderivative of the base function. So up until this point, we've been looking at f of x, right? Like if I have f of x, that's the original function, right? And with the derivative notation, we would say, oh, let's find f prime of x, right? So this is the derivative of the original. So instead of us having one more tier beneath this, we can kind of say, oh, what if I take this thing here? If I have like big f of x like this, that would be the antiderivative of the original. So we could kind of think of it as, well, if I took the derivative of the purple function, the antiderivative, where would I get to? F of x, like the base function. And then if I took the derivative of that, I would get to the first derivative of the original. And then we could keep going on, right? Like we could take the second derivative, third derivative, and so on. We could also take the antiderivative of the antiderivative. You could keep going up as well. So I'm saying, like, as we take derivatives, we're going down. If we take antiderivatives, we go up. So I kind of say up and down because when we derive something, usually we're making something smaller, especially if it's like an algebraic expression, right? Because if I keep taking the derivative, say like x cubed, if I take the derivative of that enough times, eventually you'll hit zero. Now, it's not necessarily true for all functions, right? Like trig functions, for example, it doesn't matter how many times I derive sine of x, correct? It's never going to go to zero. It's going to flip-flop between sine and cosine or negative and positive versions of that. Same thing with exponential functions. With antiderivatives, usually when you take the antiderivative of something, it's getting a little bigger every single time. So let's get more into detail about this or talk more about it. Let's say if we have this right here, like if I have, again, big F, anytime you see the big letter, like big F of X, big G of X, big whatever, T of X, they mean the antiderivative of that base function. So this right here, big F of X, let's say it's equal to X cubed, is the antiderivative of f of x equals 3x squared. Why? Why is that? Why? How can we check that out, right? How can we check that out right here? Well, remember, if we take the derivative of this, right? Because remember, big f of x denotes the antiderivative of this function right here, right? So if I were to take the derivative of x cubed, what we'll wind up with, we would get, oh, it's 3x squared, right? Right there, which is f of x. We're getting back to there, right? That's what's nice about antiderivatives and derivatives. You can sort of kind of check your work, right? Because if I take the antiderivative of 3x squared, I should get back up to x cubed, and we're going to talk about that in a second because there's rules for it. Just like how you had rules for deriving, you have rules for antiderivatives. So yeah, you can work backwards. You can check your work. You can take the antiderivative of this, and we should be able to get back up to here. Now, something unique about antiderivatives is that, and again, when you go to this case right here, so we were able to see that, oh, well, the antiderivative of 3x squared is x cubed, but x cubed is not only the only antiderivative of 3x squared, okay? So f of x equaling x cubed is not the only antiderivative of f of x, or little f of x. What do I mean by that? Well, we could also have big f of x, right? That means the antiderivative of f equals x cubed plus 4, or big f of x equals x cubed minus 19, for example. Or I could have x cubed plus a million, or x cubed minus 1/2, or whatever. Because if I take the derivative of this, right? Like if I take the derivative of this one right here, what's f prime of x in this case? Is 3x squared, right? Just like that. If I take the derivative of this one, of x cubed minus 19, what do we get? 3x squared. And again, it gets back to this base function right here. So with antiderivatives, that's something that we have to take into account. So if big f of x, that means the antiderivative of little f, right, is an antiderivative of f of x, then big f of x plus c, or I'll say plus or minus because c is just a constant, it can be positive or negative, is also an antiderivative. And sometimes when you see this f of x plus or minus c, like on WebAssign, they'll phrase it a little differently as an antiderivative. They will sometimes call it a general, or the general antiderivative of f of x. So when you're trying to find the antiderivative of a base function like f of x, there's an infinite amount of possibilities. Why? Because coming back down here, remember we saw that if f of x was 3x squared, meaning little f, then the antiderivative, we could have an infinite amount of combinations, right? Because anytime I change the constant right here, like whether he's a 4, a negative 19, a fraction, a decimal, a root, or whatever, you're creating an entire new function. But if you still take its derivative, you would still get back to 3x squared regardless. So that's why we have this plus or minus c right here. Now, you may be asking, do we ever solve or are we ever going to figure out what the C is? Yeah, later on in other sections and other maths and definitely in physics, for example, as well too, you would want to figure out what those C's are or those constants eventually. But for now, whenever they say find the general antiderivative of a function or whatever, anytime you're done taking the antiderivative, you always throw on a plus C at the end. All right. And on WebAssign, okay, very important. When it asks you for the general antiderivative of a function, when you put that plus c in the end, make sure you put an uppercase C, because if you put a lowercase, for some reason it marks it as wrong, which is ridiculous. But just please make sure y'all put plus C at the end. All right. Now another word that they use for anti-deriving is integration. Okay, so if d dx, remember that means take the derivative with respect to x of big F of x is equal to f of x, right? This is us deriving the antiderivative, which equals the base function. Then we can say this right here. This is not an S, this is the actual symbol for integration or finding the antiderivative of f of x, okay? So when y'all see this weird stretched out S, that means finding the antiderivative of this function right here. So if we take the antiderivative of little f, what do we get? We get big F plus C. Again, we're going to have this plus C right here. Now, remember, C can be positive or negative. I know I put plus or minus right here, but C, remember, if C is negative 10, then this is still positive. But for most general notation, they always just have the plus C. Now, how do you check this? Well, if I derive the right side, right? Remember, if I take the derivative of big F, what do I get back to little f? And if I take the derivative of any constant, would you get 0? So you still get back to the left-hand side, okay? So again, this means integration right here. So the process of finding the antiderivative is called integration. So again, this thing right here, this means the integral of f of x. And one more little thing I want to put in right here is this. So put in that little dx right there. So what does this dx mean? It means we're taking the antiderivative of this function with respect to x. Kind of like with derivatives, remember? If we have d dx, you're taking the derivative with respect to x. With the integral, it's the same concept. You will have some kind of function, you're taking the antiderivative with respect to some variable. It could be dx, dy, dz, d, whatever. Okay, but they will always denote that right there. So this whole process, again, when you see this, is called the integration of a function with respect to some variable. Integration just means anti-derived. Normally, they will always say find the integral of whatever. They don't usually say find the antiderivative. They say what's the integral of this or what's the integral of that right there. So again, what do these symbols mean? This weird looking S thing, that's the integral sign. We have f of x, that's this piece right here. That's called the integrand. That's the thing that you are taking the antiderivative of. Dx, as I mentioned before, is what we are integrating with respect to. And that c, that as I mentioned before, is just the constant of integration. Now there's two ways that you can see an integral written out. One is this initial way right here. This we call it, it's just an this is called the indefinite integral. This just means an integral without limits. So your answer will always have plus c at the end. And then the other possible integral that you can have is one with limits. And these we'll do later on. This is called a definite integral, just the opposite of an indefinite. So these limits a and b are actually constants. Like it would be numbers that you could plug in to your integral and you would not have a c. So you would evaluate the integral and no longer have a c. So no limits, indefinite integral, very important whenever you're taking the antiderivative or computing an indefinite integral, you will always have plus c at the end. So this holds true for the rest of your life that you do integrals, okay? And don't forget on WebAssign, when it asks you to find the antiderivative or the general antiderivative of an indefinite integral, will always have an uppercase plus t at the end when you type your answer into WebAssign. If you have numbers right here, which we'll do in a future section, you will actually get out a finite value, okay? Yeah, sometimes you can have other letters in here. You may have the definite integral from 1 to x cubed, for example, as you're evaluating, but that's something to worry about later on. For now, you'll just have numbers when we get to it, or no numbers at all, which would be an indefinite integral. So let's try out a few of these. So we saw that if f of x equals 3x squared, right, the base function, then the antiderivative, right? Remember, whenever we jump to the uppercase letter, we're talking about the antiderivative is equal to x cubed plus c. Or I'll say then the general antiderivative is big f of x equals x cubed plus c. And remember, you can check this general antiderivative. If we take the derivative of big F, we should get back to little f, right? So if I take the or if I take the derivative of x cubed plus or minus any number, right? We get back to 3x squared. If you're doing the power rule, right? Derivative of x cubed is 3x squared. Derivative of a constant, the constant, you don't care what it is, right? Because it's still 0. So we get back to here. But how are we doing that though, right? Because yeah, maybe it's easy to see with this one right here and you can kind of like play with it. But there's a specific pattern for this, right? Just like how we had the power rule for derivatives, the power rule for derivatives, right, said, oh, you take the power and you slide it out in front, right? Like if we had ddx of x to the n, right? Remember that generic rule? That was just nx to the n minus 1, right? That's us taking the derivative right here. Power rule for derivatives. Now, what if we had, and I'm going to use the integral notation. If I had the integral of x to the n dx, this means the antiderivative, right, of x to the n. So now we're going to have basically the power rule for antiderivatives. But what are we doing? Well, we're doing the reverse of this right here. So everything's like opposite. So instead of you saying x to the n minus 1, we'd have n plus 1. And instead of dropping an n down, we would divide by n like that. So this is like the power rule for antiderivatives. So you literally are doing the reverse, right? Instead of subtracting, you're adding. Instead of multiplying n, you're dividing by n. Does that hold true? Like, what if well, we can try it out with this, right? If f of x is 3x squared, right? If we wanted to find big F, we would be taking the antiderivative of this, right? So what is that? Well, what do we have to do right here? It says x to the n plus 1 over n. So we have 3, and then x to the 2 plus 1 over 2 plus 1. So remember, whatever that exponent is, you drop it down there and you add 1. And then, we have our plus c, but we keep going. So if we simplify this, what happens? We get 3x cubed over 3 plus c. And then, of course, you always want to try to simplify as much as possible. And we can, right? The 3's cancel out. So you're just left with x cubed plus c, just like that. And it doesn't matter what the exponent is or how many algebraic expressions you have. Like if I have f of x equals, and I'll say, yeah, we could say this, we could say 5x to the fourth plus 2x, for example, okay? And we want big f of x. So we want the general antiderivative of this function right here. So let's go out there, and I'm going to write it in this notation again because that's how you always see it. We want the antiderivative, or the integral of 5x to the fourth plus 2x to the first dx. And I'm putting this one here because that's important. So what do? We follow that power rule for antiderivatives. Remember, it was x to the n plus 1 over n plus 1. If you have a number out in the front, you just drag it along. So we have x to the 4 plus 1 over 4 plus 1 times that 5 plus this 2, and then x to the 1 plus 1 over the 1 plus 1. Don't forget your plus c, right? We don't have limits right here. We're looking for the general antiderivative. So we're always going to have that plus c. And then we simplify, right? Now we have 5x to the fifth over 5 plus 2x cubed over 2. I'm sorry, 2x squared plus c. And then look what happens. The 5's cancel, so you have x to the fifth. The 2's cancel right here, so you have x squared plus c. Now, how can we check this, right? So remember, with the general antiderivative, if I take the derivative of the antiderivative, I should get back to the original function. Well, what's the derivative of x to the fifth? 5x to the fourth. What's the derivative of x squared? 2x. What's the derivative of any kind of constant? 0. So you see, we were able to check our work. And you do that every single time whenever you're finding the general antiderivative. You can take the derivative of the antiderivative, and you should be able to get back to your base function. So what if I had something like this, like f of x equals x to the, we'll say 2/7, for example. Something weird, right? A fraction. Guess what? It still works out the same exact way. Just watch the powers, right? It's a fraction this time. So if we want big f of x, that's equal to the integral of x to the 2/7 dx. Well, let's go ahead and do that. X to the n plus 1 over n plus 1 plus 1. So this is x to the 2/7 plus 1, right, over 2/7 plus 1, and then plus c. So what is 2/7 plus 1? Remember, this 1, saying 2/7 plus 1 is the same thing as 2/7 plus 7/7, right? 7 over 7 is still 1. So what does this become? This becomes x to the 9/7 over 9/7 plus c. Now you're not going to leave it like this, right? A fraction thing over a fraction, a complex fraction. No. To clean it up, though, it's not difficult. It's just whenever you have something divided by a fraction, it's the same thing like multiplying that bottom fraction times the reciprocal of itself. So this is 7/9 x to the 9/7 plus c. This is what we're saying that the antiderivative of little f is right here. And we can check it, right? Let's check the fraction ones because maybe we're not comfortable with the fractions, right? How will we do that? Well, if I take the derivative of big F, right? If I take the derivative of this, I should get back to the base function right here. How's that work out? Remember, we're going to do the power rule for derivatives, which says, oh, I need to go out there and take this exponent and drop it down, right? So we're going to have 7/9 times 9/7. And then x to the 9/7 minus 1. And the derivative of a constant, right, is 0, so that's gone. So what's 7/9 times 9/7? That's 1. And then we have x. What's 9/7 minus 1? That's 2/7, which is what we got right up here, right? So you see, you can always check the antiderivative, right? Again, how do you check whether or not you got the general antiderivative correct? Well, when you take the derivative of that answer, you should get back to the base function. That only works when you have a general antiderivative or an indefinite integral. What that means is your integral has no limits right here, okay? If it has numbers right here or something else, you're not going to be able to check it that way. But for now, yes, you can go out there and take the derivative of your antiderivative, and you should get back to what you initially started with. What if I had this right here, like f of x equals 3, and we want big F of x? Again, the antiderivative of f. So we basically want the antiderivative of a constant, right? We want an antiderivative of a constant. So if we do that, this is what we want. How are we going to do that right there? How are we going to find the antiderivative of 3 with respect to x, right? Or 3 dx? Well, we're still going to do the power rule, right? It's just that we don't see an x out here. But there technically is an x, right? This is like saying 3 and then x to the 0th power, right? Dx. Because what is x to the 0? It's 1. And 1 times 3 gets it back to 3. Now, if we do our power rule, right? Well, I erased it. If we do our power rule for antiderivatives, what does that equal? That becomes 3x to the 0 plus 1 over 0 plus 1 plus c. So what does that give us? 3x to the first over 1 plus c, or just really 3x plus c. And again, we're saying, oh, this is the general antiderivative of f of x. Does that check out? What's the derivative of 3x plus the number? It's just 3, right? So the quick and easy way to remember this is for constants, if f of x equals c, then the integral of c dx is equal to just cx. And I'll put plus d, where c and d are constants. So this D is the same thing as this C right here. I just changed the letters, okay? I didn't want to put CX plus C, all right? So basically, anytime you have the antiderivative, or you're trying to find the antiderivative of some constant, you just slap an X onto it, all right? So like if f of X is equal to, say, -5, what's big F going to be, or what's the antiderivative of that going to be? It's just going to be -5x plus C, because this is just a constant by itself. Okay. But like if I had f of x equals square root of 2. What's f of x going to be? And if you want, we'll use this notation right here. We want to find the integral of root 2 dx. It's the same thing like this one right here, or what we just did previously before I erased it. It would just be root 2x plus c. So remember, how can we check this right here? If I take the derivative of this antiderivative, I should get back to the base function, which we do. What about if we had f of x equals pi? This confuses people for some reason. Remember, pi is not a variable, it's a constant. So if we were to find the antiderivative of that, or the integral of it, it's just pi x plus c. Remember, pi is a number, right? It's an irrational number, 3.14, blah, blah, blah. But if you take the derivative of pi x plus c, where do you get back to? Just pi, right? So remember, big F means the antiderivative of the base function, little f in this case. All right, so let's try this one out. A half x squared minus 2x plus 6. And we want f, big F of x. So remember, if you're going from the small letter to the big letter or the uppercase of that, that means antiderivative. So we're going to go out there and write it out with our integral notation. Because it's only in this section where they say, oh, we want to go from the small letter to the uppercase letter to denote antiderivatives. You'll always see it written like this right here. They'll always say, find the integral of this function. That's what they're going to say, not find the uppercase letter of that function. So what are we going to do? We're going to do the power rule for antiderivatives, right? What does that mean right there? Well, we're going to have 1/2 and then x to the what? 2 plus 1 over 2 plus 1, right? This thing right here. Minus 2 and then x. There's a 1 right here. So that's to the 1 plus 1 over 1 plus 1 again. Or plus 6. Now remember with this was like saying x to the 0, right? If you want to slap that in there to help you out with it, that's a constant. So this is x to the 0 plus 1 over 0 plus 1. And one more thing, don't forget it, right? Because we have an indefinite integral, or finding the general antiderivative, we're going to have a plus c. And do not forget this, okay? People always forget that on the web assign as well. They'll type in all this stuff correctly simplified, but they forget the plus c, and it says that you're incorrect. Also needs to be an uppercase c on WebAssign. So now let's go out here and simplify. This is 1/2, and this is x cubed over 3 minus 2x squared over 2 plus, and this is just 6x to the first over 1 plus c. You don't have to put this 1, right? You can just, it's assumed that there's a 1 under it if there's nothing there. So let's keep going. 1/2 times x cubed over 3 is 1/6 x cubed. And then these 2's get knocked out, so we have minus x squared plus 6x plus c. So this is all equal to the antiderivative of f. Now, how can we check this, right? How can we check, is this the correct antiderivative of, or general antiderivative of this? Well, remember, if we take the derivative of this function, we should get back to the original. What's the derivative of 1/6 x cubed? Well, that's 3 over 6 x squared. That reduces to 1/2 x squared. What's the derivative of negative x squared? Negative 2x. What's the derivative of 6x? 6. What's the derivative of c? 0. So yes, that is the correct answer right there. All right, so let's look at this one. Now, what should we do? Maybe you're thinking, is there like a product rule for antiderivatives? Well, no, there isn't. There's no quotient rule either. Antiderivatives are a lot harder to take generally over derivatives. For the derivatives, everything falls under a few rules. You have power rule, product rule, quotient rule, and chain rule. For antiderivatives, unfortunately, they don't have 3 or 4 different rules that handle 100% of all those types of problems. In fact, for some things, you can't take the antiderivative, or they're so complicated that you have to actually use a computer with some special math software to go out there and figure it out. So what can we do to make this workable right here? Since there's no product rule for antiderivatives. Well, we can multiply it, right? Let's FOIL this out. This is 2x squared minus x plus 2x minus 1. So we can say, oh, f of x is equal to 2x squared plus x minus 1. So remember, this is just the base function, right? We haven't done the antiderivative yet. I was just FOILing it out so that we can use the power rule of antiderivatives. So now f of x, big F, or the antiderivative of this, is going to be what? Well, power rule, right? Power rule for antiderivatives. This is 2x to the 2 plus 1 over 2 plus 1 plus this is x to the 1 plus 1 over 1 plus 1. And again, with this constant, right, you could say minus 1. And this is, if you need to, you can put x to the 0 right there. So this is x to the 0 plus 1 over 0 plus 1. And don't forget your plus c, right? Because we're looking for the general antiderivative. And then let's simplify that. That becomes 2x cubed over 3 plus x squared over 2. And then this just becomes minus 1x to the first over 1 plus c. And of course, you don't need this 1 on the bottom, right? You can say, oh, that's just 1x to the first or 1x. Now, is this the antiderivative of this function right here? Well, how do we check it? We derive, right? What's the derivative of 2x cubed over 3? Well, you would get 6x squared over 3. What's 6 over 3 reduced to? 2. Right here, what happens when you derive x squared over 2? When you get 2x to the first over 2. 2 over 2 reduces to 1, so you get 1x. And then what's the derivative of 1x to the first power? It's just 1, right? And the derivative of a constant is 0. What if I had something like this? F of x equals 17 over x cubed. And we want, again, the general antiderivative. So as I mentioned before, there is no, quotient rule for antiderivatives. So we have to somehow manipulate this, right? Like with the last one, we FOILed it, right? Right here, what can we do to use that power rule for antiderivatives. Well, we need to somehow get this x cubed up to the numerator, correct? How do we do that? We can make it negative, right? Remember, if I make the exponent negative, that's the same thing like me flipping it and making it positive. So now that we have it in this form, we can say, oh, we're just trying to find the integral of x to the negative, or 17x to the negative cubed dx. So now let's go out there and do the power rule. This is 17. And be careful with the negatives, right? This is negative 3 plus 1 over negative 3 plus 1. And then we have plus c. This is a big issue that people run into with anti-deriving when you have negative exponents. They'll do negative 3 minus 1 and negative 3 plus 1, or some combination of both. Like they'll derive the top but anti-derive the bottom with that. Remember, when you're taking the antiderivative, you're always adding 1. Okay, so if we carry on, we get 17x to the negative 2 power over negative 2 plus c, just like that. Now from there, what more can we do to simplify? Well, 17 over negative 2 is negative 17 halves, right? And we're going to drop that back down, drop down this negative exponent, but by doing so, we're going to flip it and make it positive. So we wind up with that right there. This plus c is not in the denominator, okay? It's still alone by itself that you're adding to this entire quantity. But again, if y'all have negative fraction or some x trapped in the denominator, you need to flip it up somehow with the negative exponent. All right, so let's look at this one. This will be the last one. So what about radicals, right? The antiderivative of radicals. Well, remember, what did we do when we were taking the derivative of radicals? We converted them into exponential form. So we need to do that right here. We should do that first. So this is just 6x to the 1/2 minus x to the 1/7, right? Remember, whatever the index is, this is a 2, right? If they don't give it to you, that becomes the denominator of your fractional exponents. So now that we have that, we can go out there and figure out the integral or antiderivative of these pieces. So it's just power rule, right? For antiderivatives. This is 6 and then x, and then we have 1/2 plus 1 over 1/2 plus 1 minus x to the 1/7 plus 1 over 1/7 plus 1. And then don't forget your c. Now, what's 1/2 plus 1? That is 3/2, right? So this is 6x to the 3/2 over 3/2 minus x. What's 1/7 plus 1? That is 8/7. So this is 8/7 over 8 over 7 plus c. Now, how do we simplify this, right? Gotta keep going with it because we have these weird fractions over fractions. Or whenever you're dividing by a fraction, that's like multiplying by its reciprocal. So what does this equal right here? This is the same thing as saying 6 times 2/3 x to the 3/2 minus, and then this is just 7/8 x to the 8/7 plus c. And watch, when you're multiplying, right, you can reduce right here. So we actually get 4, 2 times 2 is 4, x to the 3/2, minus 7/8, x to the 8/7 plus c. Now, how will we check this, right? Because this is what the general antiderivative is, right? How can we check that out right here? Especially since these have fractions. Let's say you're in doubt. Well, what's the derivative of this thing right here? So if we take the derivative of big F, right? How would we do that? You do the power rule. What would that be in this instance? You'd have 4, and then you'd have 3/2, x to the 3/2 minus 1 because we're deriving, minus 7/8. Power rule again, 8/7 because we're taking the derivative, x to the 8/7 minus 1, and the derivative of a constant is 0. So what is 4 times 3/2? Well, this reduces, right? Again, what's 2 times 3? 6. What's 3/2 minus 1? A half. What happens right here? The 7's knock out, and so do the 8's. So you have minus x. What's 8/7 minus 1? A 7. What's the derivative? Well, we already saw the derivative of the constant 0. So look, what is this? This is the base function right here. So you see, you can always check your general antiderivative. How? We take the derivative of that, right? You take the derivative of your antiderivative, and you should get back to the base function. So remember, with the fractions, the trick is to rewrite it, right? As whenever you have something, like if I have, you know, x to the 3/4 over 3/4, like something like that, that pops up. This has nothing to do with this problem, okay? It's just algebra right here. You rewrite it as 4/3, or this just becomes 4/3 x to the 3/4. You just basically flip that bottom fraction up like that. You multiply it into whatever's in the numerator. So like in this case right here, we had that 6 outside, right? So we had to multiply that 2/3 into it right there. But what's nice about these general antiderivatives is you can check them, right? How? By taking the derivative of the antiderivative, we should get back to the base function every single time. Please don't forget the plus c's for the antiderivatives, and make sure they are uppercase on WebAssign, okay? All right, that is it.